right, so we're going to look at two sections this week, 4.2 and 4.3. So what we're focusing on in Chapter 4 is rational functions. So remember, rational function, just a reminder, is a function where you have a polynomial in the top and you have a polynomial in the bottom. When we're talking about the domain of a rational function, we have to be careful that we would never divide by 0. So in this one, what value would not be in the domain? 3. Okay, we can't use 3. But the domain is everything except 3. And does anybody remember what happens at the number 3? It could be a whole, it depends. I don't know how the numerator factors, but if you don't have a common factor, let's assume that we don't.
Oh, that's right.
You would get a what? Yep, you'd get a vertical asymptote. So vertical asymptotes occur where the denominator is 0, unless you had something like this. Now, you would have two numbers that are not, or no, you just have one number that's not in the domain, -5. But -5 would not look like an asymptote. In that case, it would be a whole, because of the common factor in the top and the bottom. All right. So actually, I was just going to remind you of that. So if you have a common factor in the top and in the bottom, you can get a discontinuity that can't be seen with the calculator because it's a whole. The whole is infinitely small. The only way we would know that it's there is by looking at an equation. You cannot tell from the picture. So let's try a couple examples of graphing and just kind of remember when there is a whole and when there isn't based on what I just said. So if I graph that first, it says f of x equals x minus 1 over x minus 1. What's the domain for f of x in example 1?
All real numbers besides 1.
All real numbers besides 1. And since you're telling me 1 isn't in the domain, can you tell me what's going to happen at 1?
Is it going to be the asymptote thing? Probably not, because now it's 0 on top and 0 on the bottom.
Yeah.
So it's just a whole.
A whole. Right. There's a common factor in this case. So what's going to happen there is we're going to get a whole. So let's graph it. When you put it in, make sure you use parentheses. And when you divide x minus 1 by x minus 1, and you plug in any number you want for x except 1, what will you always get? 1. So this is basically going to look like the line y equals 1. It's going to look like a horizontal line. In fact, let me do zoom 6, so you can probably see it a little better. So it looks like the horizontal line y equals 1. But if you go to the table and you put in 1 as a value, it says error. If this really was a line, you should not get an error anywhere. So remember, the way that we show, like if you're going to graph this by hand, put a circle, open circle on the number 1, so we can see there that there's a hole. Okay, let's look at this one. X minus 1 squared over x minus 1. Okay, what's the domain of this one? Yep.
Is it just
1? No, the domain is not the number 1. Yeah?
all real numbers except 1?
All real numbers except 1 is the domain. So if I want to put this one in, I'm just going to put in an exponent of 2. And now, think of the top this way. X minus 1, x minus 1, over x minus 1. Essentially, what can I do there? I have to remember that I did this because it's part of the domain, but yeah.
You might cancel them out.
It's like you can cancel one of them out, and if you want to get a visual in your head for what this is really going to look like, it's going to look like a line with a slope of 1 and a y-intercept of -1. But you have to remember, to get that, you cross something out in the denominator that originally caused you to divide by 0. So there is still a hole in that graph. And the hole is at 1. Now, what if I did minus and I made this 1.1? I didn't change it much. I just changed 1 to 1.1.
Well, now it's going to go a lot.
Yeah, now I'm going to have an asymptote. This is going to look pretty similar on the ends, but when you get in the middle, it's going to look totally different. And again, it can't even really do it, because what's happening is it's really curving up, really, really steep. So it's really doing something like this. In fact, it's almost vertical. Because it's so vertical, the calculator, it can't even do it. And then here, it would come in and go like that. That's what it should look like. So kind of the same on the ends, but totally different in the middle. In both of those examples, before I modified it, we had what was called a hole. Well, the real word for that is called a removable discontinuity. Think of a removable discontinuity as something that can easily be fixed. An asymptote is not something that's easily fixable. Right? An asymptote is like the car has been totaled. This isn't going to be easy to fix. A hole is like, well, there's a tiny scratch. We can fix that. We can remove that and fix it. So the way we would think about a removable discontinuity is, let's pick one of the ones we had before. F of x equals, was it x minus 1 over x minus 1?
Yeah.
Okay. So what we do is we say, okay, you can use this function. Let's do it like this. You can use this top one anytime x is not equal to 1. So what we're going to do is we're going to break up the domain into 2 parts. One is going to use this formula most of the time. This is the formula I want you to use. That's the condition under which you can use it. You can use it whenever x is not equal to 1. But if x is equal to 1, what we're going to do is we're going to redefine, we're going to create a new function right here that we're going to use only for the case when x equals 1. And if we put that back in, we want to redefine it in a way that would make it continuous. So think about, if x equals 1, what would you want the formula to be so that it would be a continuous line? You would want 1. Yes. If you graph this top one everywhere x is not equal to 1, and you graph this bottom one only when x is 1, then it would actually be a complete line. So what we basically did is we patched the hole. We said, okay, most of the time you can use this one, but if you try to use the number that causes a hole, just fill in a circle at 1. Okay? So it kind of goes around the removable discontinuity. Any question on that idea? And you can do that for as many holes as you have in a graph. You could say, okay, at this hole, just fill in this number. At this hole, fill in this number. Everywhere else, use some formula that they would give you.
Okay, so it's just saying that at 1, fill in x equals 1.
Yep, I'm just saying at 1, fill in 1. And if you combine that with the behavior up above, you're going to end up drawing a perfectly straight, filled in line. Yeah. Now, an asymptote, we can't fix. Something that curves up like that and down like that, that's not even close to connecting. It's not like I just have to fix a little hole and it'll connect. That's a huge problem. So an asymptote is not considered a removable discontinuity. That's a big problem. A hole is not a big problem. Okay, so when we have two polynomials, okay, something like this. In general, you're going to be given something that has all the numbers filled in for you. This just represents some kind of polynomial in the top, starting with the highest exponent, going down 1 each time, till finally you end up with a constant. And the same thing in the bottom. We talked in section 3. Can't remember the exact section, but in chapter 3, we talked about what was called an EBM. Does anybody remember what EBM stood for? Yep.
And behavior model.
Yep, end behavior model. And when we looked at it in chapter 3, we didn't even look at it as a fraction. We just looked at it f of x equals 8x cubed, something like that. The end behavior model is the term in that polynomial that controls what the ends of the function are going to do. We had 4 options. Up, 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 down, up, down, down. Does anybody remember, by looking at f of x, what term there controls the end behavior? Most of the terms have nothing to do with it. The first one. Is it always the first one?
No. It's just the one with the largest exponent.
It's the one with the largest exponent. Should that be the first one? Usually. Yes. But it might not be. So it's the one with the highest exponent. So this particular one has an odd exponent, positive number in front. It's going to have a down, up end behavior if we were to draw it. Well, what we're going to do now is we're going to look at something like this. I want to find the EBM of a rational function. Well, to find the EBM of a rational function, you take the EBM of the top. I know this is the term with the highest exponent, the way I wrote it, because the exponents go down each time. And I can see that right there. So this would be the highest exponent term in the top. What would be the EBM for the denominator? Yep, Jiva. Hi, John.
Same thing, first term, x is the m.
Yeah, just like John said, b sub m x to the m. That's the highest degree term that's in the bottom. And now, if you want the highest degree term for the whole thing, well, you take the EBM of the top, you take the EBM in the bottom, and you divide the two. So you have to find both EBMs and then divide them. So in the top, you have a sub n x to the m. In the bottom, b sub m x to the m. And when you divide those two EBMs, they're both going to have a variable that's the same. When you have two variables that are the same, and they have exponents, and you divide them, does anyone remember what you do with the exponents? You subtract them. Yep. So what ends up happening is you have two numbers in front of the x's. Those are your coefficients. And then the exponent is n minus m. N is what's in the top, m is in the bottom. So we get 3x to the fourth over 2x to the first. And you want to divide them. Well, 3 doesn't go into 2, so we just leave that one. That's 4. That's 1. It's going to end up being x cubed. 3 halves x cubed. And that is how you find the end behavior model for a rational function. Now, just to be clear, the types of end behavior with a rational function are different than polynomials. The up, 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 down, 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 up, that's for a polynomial. Rational functions don't have those same choices. So I'll show you how we use the EDM in a minute.
Sorry, how did you get the numbers to the left?
That was just an example I made up. Yeah, that wasn't. This is going to be an actual problem. So what the EBM is used for is to figure out the horizontal asymptote. Because remember, the EBM predicts what happens as x gets bigger and bigger to the right or bigger and bigger to the left. If you can tell me what's happening at the very edges of your function, that's a horizontal asymptote, especially if it's just getting closer and closer and closer to something. Something like a parabola, well, that doesn't have an EBM. Because, well, it doesn't have an EBM that levels off, say it that way. It's just heading up to infinity. Usually rational functions do something like this. They curve, and they start to flatten out as you head further to the right. The EBM is going to tell me what this is flattening out to. That's what it will tell me. Or if I head the other way, sometimes they come up and they curve this way. The EBM will tell me what it's flattening out to as I go to the left. It's usually the same. Whatever it's flattening out to on the left is what it's going to flatten out to on the right. All right, so eventually I want to figure out what this is going to level off to. But to do that, I will find the EBM. What's the highest degree term in the top? Yep. 2x squared. What's my EBM of what's in the bottom? 3x cubed. And the method I showed you figuring this out could end up leading to negative exponents. In general, we don't want to write an answer with a negative exponent. A negative exponent just means that the variable is where? It's in the bottom. So if you end up with a negative exponent, just leave it in the bottom. So what does that simplify to? Ben?
At the top, you just have 2.
Yep.
At the bottom, you have 3x.
Perfect. There you go. Why? Well, you could think of it as x squared means x times x. X cubed means x times x times x. And then if you cancel out 2 from the top and 2 from the bottom, you're left with 2 over 3x. Okay, so that's my EBM. Now, use the EBM to predict the horizontal asymptote. How do you do that? Let x get really large and tell me what's happening. So let's go back and look at our EBM. What happens to this fraction as the x value gets bigger and bigger and bigger? this whole fraction keeps getting smaller and smaller and getting closer and closer to what number?
0. Wait, well, yeah.
0. Will it ever equal 0?
No.
No, that's the point of an asymptote. Even if x is in the millions, you're going to have 2 divided by a number in the millions. It's still not 0. It's small. Okay. So, any question on how we use the EBM to get the horizontal? Now, I kind of assume this. I started with y equals. If I had started with x equals, what would that have done? That's a vertical. But in this problem, they wanted the horizontals. Are there vertical asymptotes? I don't know, maybe. I'd have to set this equal to 0 and solve it. Which, that would be slightly annoying because it's a cubic. So I would have to hope for a rational root and then use synthetic division. So, we're not doing that. Questions on it?
Let's say it was 2x over 3. What would the horizontal asymptote be?
We'll see in 1 second. But yes, it's a good question, and that's why I have this one. Okay, so same directions. Let's start with the EBM. Okay. What's the highest degree term in the top?
2x.
And the bottom?
3x.
And what does that simplify to? 2/3. This time you have an EBM without a variable in it. That's what you were asking about. So it's the same idea. I'm going to ask you the same question. Look at the EBM. And in the EBM, let x get bigger and bigger. And I want to know what happens to the number in this box as x gets bigger and bigger.
Nothing happens to that number.
Nothing happens to that number because there is no x. So this time, my horizontal asymptote would be what? 2/3. So the question is always, what happens to the EBM as x gets bigger and bigger and bigger? If there's no x, then nothing happens to it. If there is an x, well, then it depends on where the x is. It's either going to be in the bottom, in which case you usually are approaching 0, or it's going to be in the top. That's different. Talk about that too. But any question on the EBM or the horizontal asymptote? Yes?
So, with that model of A with the subscript n over B subscript n times x with the exponent n minus m, so that would be like equivalent. You could use that same model and then it would also be equal to, for example, the 2 over 3x.
Yeah, because what you would end up with there is you'd end up with 2/3 x to the -1,
Yeah.
because you'd have a 2 minus 3. And usually what we like to do is not have a negative exponent on the variable. So if we end up with a negative exponent, which you would, in that case it just means put the variable in the bottom.
Okay. Yeah.
Yeah.
Thank you.
Other questions? So, for the rest of today, we're going to focus on sketching some of these graphs. Okay, the calculator, that's going to help us a lot. We're going to use the table on it. And for today, we're only going to focus on graphing problems where the degree of the numerator is less than or equal to the degree of the denominator. So, problem like this, the degree of the numerator is less than, yep, we'll do one like that today. Where they're equal, yes, we'll do one like that as well. When the top is bigger than the bottom, we're going to save that for tomorrow. So to graph these aren't really straight lines, they're not parabolas, they're a little bit more complicated. So there's a few different things we want to try to find. If you can, try to find where the graphs cross the x's. So find the x-intercept by plugging in 0 for y, and find the y-intercept by plugging in 0 for x. I'll tell you ahead of time, not every graph crosses the x and the y-axis. So that may not help. But if we can find it, that's a good couple points to use. Next thing we want to find are asymptotes. Doesn't really matter the order you find these things in. Just suggest. Find your vertical asymptotes. Find your horizontal asymptotes. Remember, vertical asymptotes are the zeros of the denominator, assuming you don't have a common factor. If you have a common factor, you'll get a what? A whole. Generally, I would say you could expect up to 2 vertical asymptotes in a problem. No more than that. Either 1 or 2. The EDM, that'll help you to get the horizontal asymptote. Every problem we do today will have a horizontal asymptote. I'm pretty sure. The ones we do tomorrow will not. Because when the exponent in the top becomes bigger than the exponent in the bottom, you don't get horizontal asymptotes. The next thing we want to do, and this is going to be on the calculator, is use the calculator to figure out what's happening near the asymptote. And remember, when you get close to an asymptote, you either start to approach infinity or negative infinity. Figure out which one of the two it is. Is it infinity or negative infinity? So, yep, evaluate your function near each side of the vertical asymptote. You're at a vertical asymptote at 3. I would take the graphing calculator and plug in 2.99. Tell me what happens. Plug in 3.001 and tell me what happens. Don't plug in the asymptote itself. I know what it's going to say if you do that. It's going to say error. But plug in a number close to it. And that's basically the 4 things we want to try to find when we do a sketch. So we'll try a few sketches, and then that'll be it. And you can always double check on the calculator after you're done, make sure it came out right. So there's our first one. X minus 1 over x squared minus x minus 6. What do you think that we want to do right away that will help us with finding the zeros of the denominator? Yep. You want to factor this. Hopefully this will be quadratic most of the time, because then you can find the zeros pretty quickly. If it's cubic, it could take a while. Okay, but quadratic, that's pretty quick. How does x squared minus x minus 6 factor?
X minus 3x plus 2.
X minus 3, x plus 2. Now, factoring isn't the best way to write it to figure everything out, but it is the best way to write it to figure out the zeros of the denominator. So when we get to that step, at least we already have it factored. All right, let's start with our intercepts. Let's do the y-intercept first. To find the y-intercept, can someone remind me what number do you plug in?
X. Right?
Well, what?
No, sorry.
Plug in 0 for
X.
x. Okay. What do you get in the numerator if you plug in 0? And in the denominator? -6. Okay, so the y-intercept is at 1/6. So it's going to cross the y-axis. Right about there. It's not enough information to graph it, but at least it's 1 point. We need more. Okay, let's do the x-intercept. That's when you do what?
Plug in 0 for y.
Plug in 0 for y. So that's basically when you make that a 0. That's how you plug in 0 for y. Change f of x to 0. Now, if you did that, you'd have 0 equals, and then you'd have a fraction. What's the only way that a fraction can come out to 0? If
Denominator is equal to 0.
if the denominator is 0, it would be undefined. If the numerator is 0. So all we have to do to set this equal to 0, which basically means we just changed y to 0, is figure out what would make the top 0. And that's my other intercept. So take the top, set it equal to 0, and you get an x-intercept of 1. Okay, so we got 2 points. What's going to start to give us a lot more information than the intercepts? I mean, the intercepts are good, but what's going to give us a lot more is the asymptotes. So let's find the vertical asymptotes. How many vertical asymptotes do we have?
2.
2. And what numbers are they at? 3 and -2. So 3 and -2. Any question on the vertical asymptotes?
So, alright, you're plugging those in the factor.
Yeah, I'm looking at the factored form of that quadratic in the bottom and looking at what would make it 0. Those are the zeros of my denominator. And when I factor it, I should have pointed this out. Any common factors here? No, then there's no holes in this graph. All right, let's sketch those 2 asymptotes as vertical lines. Just made it smaller so I can do this easier. So -2 and +3. Okay, so there's my asymptotes, verticals. Let's do the EBM. To find the EBM, it's better to have this foiled out because you need to see the highest degree term in the top and the bottom, and the original is better for it. So what's my EBM of f of x? Okay.
1 over x.
It's going to be 1 over x. Now, the important thing is, let x get really, really big, and tell me what happens to that fraction. It gets closer and closer to 0. So that's my horizontal. Dotted line at y equals 0. Because my axis is already black, do that in red. And that's a pretty typical kind of shape we get. So we basically just split the plane up using the asymptotes, almost like tic-tac-toe. We got like 6 different areas.
Wait, sorry, how do we get the red line?
That's the horizontal asymptote y equals 0, because that's what happens to the EBM as x gets really big. All right. Now, what after we draw the asymptotes, what was step 4? And where do we want to evaluate it?
Near each side of the positive.
Right, near each side of the -2 and +3. You don't need to do this on the calculator, but I would rather be able to use the table and type numbers in faster than plugging in numbers into the original formula. All right, so we've got x minus 1 divided by x squared minus x minus 6. Okay, so what would be a good number to plug in if we want to check out what's happening when close to 3? Yep.
2.99.
Yeah, let's check out 2.99. Right, I'm at -400. Okay, so we'll put that on the graph in a minute. What's another good number near 3?
3.001.
So 3.001 on that positive 400. And what would be two other good numbers to pick near my other asymptote? Christian?
-2.001.
001. Okay, I'm at -600. And can you give me a number on the other side?
-1.99.
And I'm at +60. Okay, so we can see that. Don't worry about the other numbers; those are just from another problem. Let's graph those the best we can. Just before the number 3, we're down at -infinity. So just before 3, put your point way down. Just after 3, put your point way up at +infinity. Now do the same thing for the -2 point. What was the other one? -2. Just after -2, I'm down at -600. So just after, I'm way down. And just before it, I am way up. Okay, so at this point, once you start to know what these things look like, you would be able to just sketch it. If you're not sure, pick another point. Like, if you want to know like what's happening over here, let x equal 10. That's a point that's still on my graph. And I get 10.107. Just barely above the axis. And then if I do -10, well, I get a point that's just barely under the axis, -0.1. So let's start in this lower left section. Anybody have an idea what that lower left part is going to look like? Yeah?
It's going to be right and immediately go down.
Yeah, it's going to go to the right, then it's going to just drop off completely. So it's going to stay very close to the asymptote, but then all of a sudden you can't keep going right because it runs into another asymptote. So that's what's happening in the lower left. How about the upper right part? Anyone have an idea what's happening there? Yeah?
It's going from that rightmost point and then approaching +3 from the positive side, but then never reaching there.
And what happens to the y value as we approach 3?
It gets greater.
It gets greater. So the only thing that's left is the middle. Well, I can kind of see because I have 4 points in the middle right now. 1, 2, 3, 4. All those points have to connect and it has to stay within those asymptotes. So it's going to stay as close as it can to this one. But then all of a sudden it starts to curve and then it curves again. And that's a pretty standard kind of picture that you get when you do these functions. Part in the middle that kind of has an S shape, and then two curves in the upper right and the lower left. Let's graph it and see how we do. I think our curve in the middle should have been a little flatter. That's okay. I mean, it's still a really good sketch. That's basically what it looks like. All right. Any questions on that? So it's really the asymptotes that help us, because those dotted lines are like our guides for where we're going to sketch things. And remember, you get closer and closer to them, but you never cross them. It's okay to cross it in the middle, because this horizontal asymptote has no meaning near the origin. It has meaning when x is in the millions or billions, not when x is like 1, 2, or 3. Yep.
Does this mean homework's going to have sketching and if so, do you have graph paper?
Yeah, I have some graph paper you can, I think, yeah, there's a bunch on the back there if you need it. If you can sketch it without it, that's fine, because really all you need to do is draw asymptotes.
Okay.
So you could do it on blank paper, but it might be easier on graph paper for some people.
What are we going to do for like homework answers tomorrow? Are you just going to read what the...
Well, yeah, I can read the
EDM and
can read the asymptotes, the EDM, the intercepts. I just can't really show the sketch. I can always do that. Or I could put the picture on the screen too from my camera. I could do it that way.
Oh, where did we get the two points far left and far right? That infinity and negative infinity almost?
This one
Yeah.
and this one?
Yeah.
Oh, I plugged in -10 and 10 because that was the left and right edge of my graph paper.
Oh, okay.
If my graph paper went to 5 and 5, I probably would have done those two.
Oh.
And I could check and see how accurate I was in here. Like I could plug in 2, and it should be about 1.5 based on my graph. Might not be exact, but hopefully it's pretty close.
If you plug in a number that, like, let's say you plug in y equals 3, will it give you both what x values would be?
No, when you use the table, you can't fill in a number in the y column and get the x. You can only fill in a number in the x and get the y. Even though if you go to table setup, there's a setting to have it do that, it doesn't work. It just doesn't work. But yeah, for certain y values, there is definitely more than one x. Like when y is 3, you're here, and you're here. So you get more than one. Any other questions on that? Alright, so we got that one.
Could you just type in normally for inputting a fraction just like normally to the calculator? Sometimes trying wasn't working.
For putting in a fraction? Yeah, usually you have to put it in parentheses, but that's it. Okay, so when I start to look at this one right away, a couple things I notice. The degree of the exponent, the highest one in the top and the bottom, they're both 2's, which means you're going to get a horizontal asymptote, but it will not be at 0. The other thing I noticed, the denominator should probably be factored, and it's not as complicated kind of factoring as the last one. Does anyone see what you could factor out of 2x squared minus 5x? Just x. And what would that leave you with when you factor that out? 2x minus 5. Okay, so let's do our vertical asymptotes. What numbers could you plug in for x?
Where and then range stays the same.
Yeah, you would stay the same. Yeah. What could you plug in for x to make the denominator 0? 0. And? 2.5. Okay, so we'll do those in a little bit.
Yeah, how do you have to put the intercepts first?
Yeah, well, I think I wrote those down after. So whatever order you want to do them in, it doesn't matter. Okay, what do we always use to find the horizontal asymptote? What do we find first? Find the EDM. So So let's EBM. What's my EBM in this case? Yep. 3 halves. Not y equals 3 halves, just 3 halves. Now, my horizontal asymptote, what happens to that number as x gets bigger and bigger? Stays the same. So what's my horizontal asymptote? Well, 3 halves is the EBM. How do you properly write an asymptote? Okay. It's got to be an equation. Okay. So we've got our asymptotes. That's what's going to divide our graph up into a grid. So now we've got an upper left, a lower right, and a middle. Let's start with the y-intercept. What are you supposed to plug in for the y-intercept? You're supposed to let x equal 0. But what happens if you let x equal 0 in that problem? You divide by 0. That's at a vertical asymptote. So this problem, it doesn't have a y-intercept. You can't plug 0 in for x. Okay, I'm not going to worry about the x-intercept this time because, we could find it. The annoying thing is, to find the x-intercept, you have to set the numerator equal to 0. So I have to do quadratic form. I could do it. Right? It's not impossible. It's just, for the amount of information it's going to give me and the amount of time it's going to take to do it, I don't need it for this problem. That's everything then. Let's graph it. So vertical asymptotes at 0 and 2.5. I'm just going to make it fit so I can see it. And then I'll make it bigger again. So we have 1 at 0, 2.5. And we have a horizontal. So let's put in the 0. Let's put in 2.5. And where was the horizontal? 3 halves, so 1.5. There we go. So we're going to have 3 pieces to this graph, just like the last.
Where was this, sir? Oh, 3 halves.
Okay, what do I want to do now, which I could do by hand, but it's faster if I use the calculator to do it. Thank you. Yep.
Plot those points near the vertical asymptotes.
Right, plot some points near the asymptotes to get an idea of what's going on. So we've got 3x squared plus x minus 4. Again, make sure you put that in parentheses. And then put in divided by 2x squared minus 5x. Could you type in the factored form of the denominator and get the same graph? John? Yeah, of course you should, because if these aren't equal to each other, then you've changed the problem, which that's not right. So yeah, you could type in the factored form. It'd be more parentheses, so it's easier to go back to the original. Okay, let's pick some values. Again, you can clear these out if you want. You don't have to, because they're going to just get overwritten anyway when you type in new numbers. All right, what would be some x values that I should put into my calculator? 10? 0.001. Yep, that's a good one. We're up at 800. What would be another good value?
Negative 0.001.
Yep, that's a good one. And we should be down, way down. I did negative 0.0001. That's fine. Right? Negative 8,000. All right, and 2 more values near my asymptotes. 2.499. Okay, good. Up at down at negative 3,448. Yep.
And 2.501.
01. And we're up at 3,451. So the point is that the asymptotes, it should go way up and way down. I guess they could both go up. All right, so just to the left of 0 we're going to be way up. To the right of 0, to the right of 0, we're way up. To the left of 0, we are way down. To the left of 2.5, way down. To the right of 2.5, way up. And if you want to get points on the edge of your graph paper, you could do 10 and negative 10. But I can tell you, if you do 10, it's probably going to end up being like right about there. Probably like just above that line. This is supposed to be at 1.5. So it's probably going to be like 1.51. It's going to be just above it. If you want to check it, just type in 10. Oh yeah, it's still up above it as you go. Let's go even further out. Now we're getting closer, 1.6. And by the time you get to 100, it's at about 1.5. Okay, so it's leveling off at 1.5 as you go to the right. It's also going to level off at 1.5 as you go to the left. Okay, so this one looks pretty much identical to the last one. It's got a curve in this section. Comes down. It's got a curve in the upper right. It stays close and then starts to curve out. And in the middle, I don't really have a lot of points there. I only have 2. What's another x value I could plug in to maybe get 1 or 2 more points in this middle section? Yeah, we could do 1. So when x is 1, we're at 0. So 1, 0. We could do 2. It's going to start getting pretty far down. So 2, negative 5. So 2, 1, 2, 3, 4, 5. Okay, I think I got enough to see what's going on. This middle section is very steep.
Yeah.
So it's going to come down, stay very close, until all of a sudden it starts to curve just a little, and then it keeps going down. In fact, that middle section is so steep this time, I don't think the calculator is going to be able to draw it. It's too steep. It's going to look like it just stops in the middle. It actually, the same problem happened as it goes down in that lower left. It starts to go down so steep that it looks like it just stops. Okay, but really it should look more like what we have right here. Any question on that? All right. Last one. So why don't you guys try that one? It's x minus 2 over x squared minus 2x minus 3. Okay, find all the different things you need to find and see if you can make a sketch. Okay, so let's start to take a look at it. And again, I think the intercepts are pretty straightforward to find here, especially the numerator being linear. It makes the numerator very easy to figure out when it's 0. Okay, so speaking of when the numerator is 0, what would my x-intercept be? Yep, 2. So the x-intercept occurs when x equals 2. So we're going to cross the axis right there. How about my y-intercept? Yep.
2/3.
2/3. If you fill in 0 for the top and the bottom, you'll get negative 2 over negative 3. So 2/3. Again, I can start to see that S curve that's going to happen.
Wait, sorry, was it 2?
Because that's what you get when you fill in 0 for x. Negative 2 in the top, negative 3 in the bottom. Vertical asymptotes. If you factor it, you'll be able to see what these are. What did we get for vertical asymptotes?
2.
I'm not sure both of those would be right. Yep. 3 and -1. Okay. And I checked these earlier on the calculator. So 3 and -1. So we've got those. What's my EBM this time? Yep.
1x.
No, not 1x. Yep.
1/3.
1/x. Which gives me the information to figure out my horizontal asymptote. So, Xander, what's my horizontal asymptote? So how do we use the EBM to find the horizontal asymptote?
What happens when x in the power of x increases?
Yes.
So it doesn't sorry, the value gets smaller as x increases.
And what does it approach?
It would approach 0.
It would approach 0. So the horizontal asymptote is at 0. All right, so put in your asymptotes, and then I already have some points that I plugged in, and then we'll use those to figure out what happens near the asymptotes. All right, let's put that there. Okay, so horizontal, y equals 0. Again, perfectly fine for it to cross the horizontal asymptote near the origin. No problem. Vertical at 3 and -1. All right, let's just look at what happens. When you are just to the left of -1, you're going to be down at -infinity. To the right, you're going to be up at +infinity. Just to the left of 3, you should be way down. To the right, way up. I don't really need to check any more points. If you need to check more points, that's fine. But this is the idea of what's going to happen. So it's going to curve just like that in the lower left, upper right. Going to do something like that. In the middle, you're going to get that kind of S shape. Okay, I'm not sure. Let's see how the calculator does. I think it'll do a little better with this one than the last one. Yeah. It was able to draw it the way that it should look. That's it. All right, so any questions on sketching rational functions, at least where the degree in the bottom is equal to the top, or the degree in the bottom was, well, we did equal, and then we did where the degree was larger in the bottom. Okay, so tomorrow we'll look at what happens when the degree in the top is larger. All right, so that's homework for tonight. Okay, you've got about 6 or 7 minutes. So if you need to come talk to me about anything, now is a good time. Question?
Are you going to take